All right, today we are cracking the code on one of the most fundamental ideas in all of technology, algorithms. You know, they're kind of the invisible engines that are driving pretty much everything, from your social media feed to global finance. But what are they really? And why does the way they're designed matter so much? Let's dive in and crack this thing open.
So let's kick things off with a big question, one that gets right to the heart of everything we're talking about today. Imagine you have the fastest computer ever built, with, like, infinite memory, a total beast of a machine. Does the software part, the actual intelligence of the instructions you give it, even matter anymore? Well, the answer might just surprise you.
Okay, so let's get a clear definition on the table. At its core, an algorithm is, well, it's just a recipe. As you can see here, it's a finite set of instructions. It's the blueprint, the pure strategy that a computer follows to get something done. Think of it this way. It exists long before anyone ever writes a single line of code.
Now, we tend to think of algorithms as this super modern Silicon Valley invention, right? But where did the idea actually come from? Well, it turns out its roots go way back. They're ancient, and they laid the foundation for all of computing as we know it.
The word itself, it actually comes from a 9th century mathematician, Al-Khwarizmi. Now, fast forward through a few centuries, you have pioneers like Ada Lovelace writing the first ever algorithm for a machine. But the real game changer, that was Alan Turing in the 1930s. He created the theoretical groundwork for what a computer can even do. And just a couple of decades later, boom, the first digital computers were built. And these abstract recipes became practical, world-changing tools.
Which brings us right back to that first question we asked. With all this crazy computing power we have now, does the quality of the recipe still matter? And the answer is a huge, emphatic yes. Because, as we're about to see, not all algorithms are created equal, not even close. Let me give you a really simple analogy. Imagine you have to find the name Smith in a massive alphabetized phone book. How would you do it? Your strategy, your algorithm, is absolutely everything here.
So, on one hand, you've got what's called a linear search. This is the brute force way. You start at page 1 and you just keep turning pages. I mean, yeah, it works eventually, but it totally ignores the fact that the book is sorted. But then you have the brilliant binary search. You jump right to the middle of the book. Is Smith before or after this point? Boom! You just eliminated half the entire book in one shot. You do it again and again, slicing the problem in half each time. It's not just a little faster, it's unbelievably faster.
And this quote just nails the point perfectly. A supercomputer running that dumb page-by-page linear search could easily get crushed by a basic little laptop running the intelligent divide-and-conquer binary search. The strategy is so much more important than the raw speed.
Okay, so if the strategy is that important, how do we actually measure it? How do computer scientists talk about and compare different recipes in a standard way? Well, it turns out they have a special language just for this.
You see, the key question isn't just, how long does this take on my computer? It's about how its runtime grows as the problem gets bigger and bigger. As the phone book goes from 100 pages to 1 billion pages. And let me tell you, the difference is staggering. Just look at this chart. An efficient algorithm, like our binary search, is logarithmic. That bar on the left, its runtime barely goes up at all. A linear one grows steadily, which is okay, but look at that quadratic one on the right. If you just double the amount of data, the time it takes quadruples. With the massive data sets that power our world today, that kind of algorithm isn't just slow, it's completely unusable.
This formal language is called asymptotic notation, but you'll almost always hear it called Big O notation. Now, don't let the fancy name scare you. All it really is a way to describe the worst-case scenario. It's like giving an algorithm a grade, A, C, or F, based not on its speed on one specific machine, but on how its performance scales as the problem gets massive. It's the universal measuring stick for efficiency. So, we've seen that we can measure and find efficient algorithms for a lot of things. But what happens when, for some problems, no efficient algorithm seems to exist at all? This is where we get to the really fascinating stuff, the very frontier of what's even possible with computers. To get a handle on these hard problems, we need to understand how computer scientists divide them into two big categories. First, You've got P problems. These are the easy ones, where finding a solution is fast. Think sorting a list of numbers. But then, there are NP problems. And for these, finding a solution might be insanely hard, but, and this is the absolute key, checking if a proposed solution is right is super easy. It's like a Sudoku puzzle. Solving it from scratch is tough, but checking a finished one, that's a piece of cake.
So first up, we have the class P for polynomial time. The simple way to think about P is that it's the club for all the problems we consider efficiently solvable. These are the good ones, where the runtime doesn't explode when the data gets bigger. They're manageable. Then we have the class NP. Now, the name is a bit of a mouthful, but the idea is actually pretty simple. It's the set of problems where a potential solution is easy to verify. Finding the absolute shortest route for a delivery truck visiting 100 cities is brutally difficult. But if I give you a route, you can check if it's under a certain mileage very, very easily. That's the core difference. Hard to solve, easy to check.
And this very distinction between P and NP leads us to the single biggest unanswered question in all of computer science. It's a mystery so profound that solving it could literally change the world as we know it. See, inside this big group of hard NP problems, there's this special little subset called NP-complete. These are the absolute hardest of the hard, the monsters. They're also deeply interconnected that if you could find a fast, efficient algorithm for just one of them, you would automatically have a fast algorithm for every single problem in NP. It's like finding a single master key that somehow unlocks thousands of different impossible-looking locks all at once.
So, how do scientists actually prove a new problem is one of these super hard ones? They use this really clever trick called reduction. Think of it like this. If I can show you that solving your new weird puzzle is basically the same as solving a known impossible puzzle like the traveling salesman, then I've just proven that your puzzle is also impossible to solve efficiently. It's how they sort these problems into the hard pile.
This question of whether P equals NP, whether every problem that's easy to check is also secretly easy to solve, is one of the most important questions in all of science. It's so big, in fact, that it's one of the 7 Millennium Prize problems. There's a $1 million prize just waiting for whoever can come up with a proof.
So why should you care about this $1 million math problem? Well, because the entire security of the internet and all of modern cryptography is built on one giant assumption, that P does not equal NP. The ways we protect your bank account, your private messages, all of it relies on certain problems being incredibly hard to solve.
And that leaves us with a final, kind of mind-bending thought. If someone proved tomorrow that P does equal NP, it would shatter modern cybersecurity in an instant. But it could also unlock unimaginable progress in medicine, logistics, and artificial intelligence. So the real question is, what do you think that world would even look like?